Hello, Algebra 2 students. Today we are going to be reviewing for tomorrow's Unit 8 test, covering all of the information that we've been doing for the last 2.5 weeks on the exponential functions. Now, the exponential functions did a little bit more than some of the other functions, had a little bit more applications, so we are liable to face more word-type problems on the test than we have in the past. However, the function itself works much the same way as several of the other functions have. Just a couple of new little twists and turns for us to pay attention to with the equation itself. Okay, so we started 2.5 weeks ago looking at the basics of the function. Okay, so we came up with a basic equation for the parent exponential function. You can see it there in the center of the screen. Y equals b to the x. Now, b just simply represented a base, and x represents an exponent. Okay, that's the official vocabulary, a base raised to an exponent. Okay, but b is simply some type of a constant. And as we have hopefully been refreshing our memories here lately, the base is typically a value, well, at least in the parent function, it is a value larger than 0 and not allowed to be 1. And if you haven't figured that out yet, the reason why it is not allowed to be a 1 is when the base is a 1, actually the only thing that is graphed is a horizontal line. So you don't get that horizontal to one side and vertical to the other side if b happens to actually be a 1. Okay, so it doesn't really graph an exponential curve, and that's how come they didn't allow us to have that b number equal to 1. Anyway, the parent exponential function moves along the negative x-axis in quadrant 2, passes through 1 on the y-axis, and then turns upwards in quadrant 1. And so we kind of started with a basic equation of y equals 2 to the x, but of course the base did not have to be a 2. As long as it was a positive value and was not a 1, then any base number that fit those qualifications could be considered the parent function. So this was the first graph we've really seen where the parent function could actually have some different appearances. We had grown accustomed to the parent function being one specific graph and only that graph. The exponential equation is a little bit different. And hopefully, as you are well aware by now, the domain of the exponential functions is all real numbers. It goes from negative infinity to positive infinity, covering the entire x-axis. And the range will only go to infinity in one direction. So the range will either come from negative infinity and stop at a particular asymptote, or it will begin at a particular asymptote and then move off to positive infinity. And we'll take a little bit of a look more at that here in a little bit. Okay. One of the things that we have kind of worked on, or we've at least stressed it several times, and a lot of you have managed to ignore this information throughout the entire unit, is of course the nature of the exponential function. It is horizontal in one direction, it is vertical in the other direction. It does you absolutely no good to look at whole numbers in both of those directions. Okay, so for those of you that have managed to simply ignore that and just continue to pick on whole numbers on the vertical side of this graph, you are absolutely missing the point. And it's time for you to recognize we got to learn to read this equation correctly so that we know which side of the graph is going to be vertical, so that we can pick some step sizes that actually make some sense, rather than just hoping the calculator's table spits out numbers that we can use. It's not difficult. Simply get it done. Okay, so what we did is we spent a little bit of time looking at the parent function. Of course, starting point has been critical to us all along. Just like any graph, you got to know where to begin. If you're looking at the parent function, then we know that it's going to cross at 0, 1. We know that the parent function is going to go horizontal to the left from there, vertical to the right from there. So as we move to the left from 0 on the x-axis in the domain, we picked whole steps, okay, big steps, because we're not worried about much vertical change as we go along the horizontal side of this graph. Going to the vertical side of the graph to the right, okay, we are worried about the vertical changes, so we take smaller domain steps to see what's going on in the range. How do you get the y values that go with these x values? No, you don't type it into your calculator and see what the chart says about it, because the chart does not always answer the questions that we need to answer on the test. We're going to plug these values in one at a time. Take -3, plug it in for x, and find out what 2 to the -3 power is. It's not that difficult. Then take -2, plug it in for x, find out what 2 raised to the -2 power is. It's not that difficult. Then do that for -1 and do it for +1/2 and do it for +1, and you get values. Some of y'all keep wondering how come you keep missing the same questions on these tests time and again. It's because you think the calculator's chart is actually a good thing. It's not. Learn to plug a value into an equation and find out what the other value is. That's how these tests keep beating you. At any rate, once you have your ordered pairs, you got your points. Once you have your points, you have your graph, and it's really not a big problem. Okay, so there is at least one version of the parent function. That's what we did on the first day. The next day we came back and started looking at some of the equations. Okay, so we saw that we have several changes that can be made to the parent function. Just like always, we have an h value that can move our x coordinate of our starting point. We have a k value that can move our y value of our starting point. And then, of course, we have some constants that can directly change y or directly change x or possibly turn graphs backwards or upside down and stuff like that. And we need to know how to read those things. Okay, so H causes a horizontal shift, K causes a vertical shift, A can compress or stretch the graph vertically, C can compress or stretch the graph horizontally, and as we saw later on, we had a little bit of difficulty trying to figure out which way it's been compressed or stretched, and the good news is you probably won't have to know which direction, whether it's the X or the Y that's been compressed or stretched. You'll simply have to know that the graph has been compressed or stretched in one of the two directions. Okay, so I gave you some basic pictorial representations here, showed you what happens. One of the big things that happens is if the base number in the exponential equation manages to be between 0 and 1 on the number line, that actually causes the graph to reverse directions. So instead of being horizontal to the left and vertical to the right, like it is on the upper right picture there, okay, that's what we're used to seeing with the parent function. A different version of the parent function could cause it to look like that left picture when we're between 0 and 1 on the number line in the base. If we get larger than 1, of course, we get the horizontal to the left and vertical to the right. Same things are true when we get to the negative side of the number line with the base. However, if we're on the negative side of the number line with the base, then of course the graph is going to be upside down. Now the constant c can be changed in front of x there. Okay, if c is changed to a value smaller than 1, then the graph becomes slower. When the value of c is 1, that is the standard speed of the graph in the parent function. And when c gets larger than 1, that increases the speed of the graph. Okay, same thing is true when we get to the negative side of the number line with that constant. If it is between -1 and 0, okay, the graph is backwards, but still slower. When c is -1, we got the standard speed, but the graph is backwards. When c is smaller than -1, meaning from -1 off to the left towards -infinity, that means we got a faster graph, but yet it is backwards because it's negative. Okay, we walked through some examples on how to do those things. I'll just give you the basics. Okay, remember you got to have somewhere to start. That's going to be important. Remember that the starting point for these graphs is not the origin. The starting point wants to be either at +1 on the y-axis if the graph is right side up, or -1 on the y-axis if the graph is upside down. From those locations, you move according to h and k. For example, this graph, right side up, it wants to cross the y-axis at +1, but h and k are not going to allow that. From +1, our graph is moved 2 units to the right and 3 units up. So instead of being at 0, 1, it is 2 units to the right, 3 units up. That puts it at 2, 4. That's important. When you begin your graph, you need to begin in the right place. Then read the equation. Decide, is the graph going the direction that we expect, meaning horizontal to the left and vertical to the right, or is it running backwards? Our base, the base number is between 0 and 1. That's going to cause it to run backwards. So we are vertical to the left, horizontal to the right. That's important when you go to pick values to plug in. Okay, we want to take small steps going to the left, larger steps going to the right. Okay, so pick values that make sense. Okay, there's other examples that are in there. Okay, the next thing that we did after we took a day to do everybody's favorite activity up on the walls was we came back and we looked at inequalities dealing with the exponential function. Now what we saw in this one is it was not a real big challenge to deal with the inequalities. Hang on, my file's having trouble here. There we go. And as always, of course, we said any points that exist on an equation or on a graph are solutions for the equation of that graph. But of course, when our equation turns into an inequality, not only are the points that are on the graph possibly solutions for the equation, but also it divides our Cartesian plane into two areas of space, and all of the points that exist in the appropriate area of space are also solutions for the inequality. Okay. At any rate, just the quick review here again, same rules still apply that have always applied. If you have a variable already isolated, it's very easy to deal with the equation. Simply read the direction and axis of the equation. If the equation says y is greater than or equal to, like it does on the left there, then that means you shade from the curve towards the greater values of y. That would be upwards. Or like the one on the right, y is smaller than or equal to. You shade from the curve towards the smaller values of y. That would be downward. And the same thing would be true of x. If we had an equation that said x is less than, then you shade from the curve towards the smaller values of x. If it says x is greater than, you shade from the curve towards the larger values of x. If a variable is not already isolated, and you feel like you can isolate it easily without messing anything up, then go ahead and do that. And then you can read the inequality just like at the top. And of course, if you run into a problem with an equation, or you're just not real sure about it, you can always pick a test point in open space, some value x comma y, plug it into the inequality. If the inequality reads correctly, you end up with a true statement, then that means the inequality liked that point, shade toward it. And if you end up with a false statement, then that means the inequality did not like that point, shade away from it. Okay, so I gave you some examples on that. The next information that we got into were the different types of growth and decay problems. And it doesn't take a real rocket scientist to realize that this is probably where we ought to be the most concerned with our problems, because the exponential equation does have direct applications on these type of problems. So I think it's very likely that we may face several questions dealing with these type of word problem situations. But we'll see. The tests have kind of surprised us here lately, but if I were constructing the test, I would probably make sure that there are at least a couple of setup type problems dealing with incremental growth and decay, and then continuous growth and decay, and then possibly make you answer 2 or 3 questions about each of those word problems. But we'll see when the test gets here. At any rate, we have 2 formulas that we need to make sure that we can operate within. But I think as many of you have seen, the real challenge is not necessarily working with the formula. Surprisingly, a lot of you seem to be having trouble figuring out which formula to use under which times. And I think that partly has to do with the fact that when we were working the problems on incremental growth and decay, well, first off, we weren't really paying a whole lot of attention to the problems or the formula because we were busy copying down what the sub wrote. And secondly, we're not really thinking about the problems. We weren't really looking at the problems going, okay, I see that this is an incremental growth problem because I see the way that it is constructed. We were simply using the incremental growth formula because it was on the incremental growth worksheet. worksheet, and then we use the continuous growth formula because it was on the continuous growth worksheet. Well, guys, as always, the problems are not going to come out and say, pick me, I am this particular type of problem, so you must use this formula. It's going to be up to you to decide which formula you should use. Okay, so after examining a problem and figuring out that you are actually looking at a problem that deals with incremental growth, and that means that, yes, a certain time period is going by, and then something happens. Then the same period of time goes by, and then the things happens again. That is incremental, and the formula, as you can see in the center of the screen there, is y equals a times b to the x. Now the variables represent a is the initial amount of whatever it is that the problem is doing. B represents the rate of growth. Now, please keep in mind that on the incremental formula, the rate of growth B is in the base. If it is in the base, then the equilibrium point, kind of the place where decay and growth are separated from each other, is at the value 1. As you increase from 1 going to the right on the number line, that indicates growth. As you go to the left from 1 on the number line, that indicates decay. So when it comes time to figure out what your B value is and plug it into the formula, you need to make sure that you begin at 1 and then increase from there or decrease from there as is appropriate. X represents time in the problem. Again, time always gets the x-axis. It is always the independent variable when it is present in the problem. Okay, so X represents time. And the Y side of the equation represents the amount that will happen after a certain amount of time has gone by. Okay, the rest of this lesson was simply plugging in numbers for A and B and X and getting the value for Y. After that, we went to the continuous growth and decay formula. And again, the problems are typically not going to come out and say, hey, I am continuous. Use the continuous formula. It'll be up to you to make that decision that a problem has a certain amount of time going by, but whatever is happening in the problem is always happening. It just happens over that particular time period, and then it'll continue to happen again over the next time period. It does not wait for time to go by and then occur. It's happening all the time over a certain period of time. Now, some problems will come out and tell you that they are continuous, but not all of them, so pay attention. Once you decide that a problem is a continuous growth or decay, we have a different formula. It is A times e to the kx. Okay, now the variables A still represents the initial amount of whatever's happening in the problem. E is known as Euler's constant. It is a number, okay, an irrational number that exists in the mathematical world. Our calculator knows what this number is. It is in the ballpark of 2.82. Okay, but we can use E on our calculator. K represents the constant of proportionality. This is similar to the rate of growth from the other formula that we had, but please notice that in this case, our value, rate of growth, or constant of proportionality, whatever they want to call it, is in the exponent. Okay, if it's in the exponent, then 1 is no longer the value of its equilibrium. 0 is its starting point, and then as you increase from 0, that indicates growth, and decrease from 0, that indicates decay. Okay, so make sure that when it comes time to figure out that value and plug it in, make sure that 0 is the starting point and adjust towards the negative numbers for decay, adjust towards the positive numbers for growth. X still represents the amount of time that has gone by, and of course the Y side of the equation still represents what the problem will be doing after a certain amount of time has gone by. Then the last lesson that we looked at dealt with more advanced growth and decay problems. Now, it's not that the problems themselves got more advanced, it's more that the math inside of the problems got a little bit more advanced. And what ultimately happened was on the previous two lessons, we were looking at problems where everything was already provided for us. The rate of growth, the initial amount, the time that went by, all of that stuff was presented to us in the problem, and we just had to solve for what was going to happen on the left side of the problem. What was the future amount going to be after a certain amount of time went by? Well, these are just variables, and just like any variables, it might be any one of them that is unknown. So on these problems, we were being given what future amount we were going to have after time went by, but time might have been unknown, or the initial amount might have been unknown, or the rate of growth might have been unknown. So we have to be able to solve for those variables as well. Okay, and I'm just going to jump straight to the summary screen that I had put up in class. You can look back at the examples in those lessons if you need to. Okay, but in summary, we picked up a couple of new math skills, and one of them dealt with, like the yellow font at the top of the screen here, and that dealt with getting an exponent off of an unknown base. Okay, so let's say we had, in this case, a b raised to some power, and we needed that power off of our b. Okay, well, one of the ways we could do this was to utilize law 3 of the laws of exponents, which basically said a power raised to a power means that you multiply those two exponents. So we use this fact against the problem by bringing a new exponent in that was the reciprocal of the exponent that we didn't want. And that's how come you can see there in the white type that's on the screen, you've got the exponent attached to b there, which is whatever number it is, and then the new exponent that we bring into the problem is the reciprocal of that exponent. And some of you are still forgetting one of the main cardinal rules of Algebra 1. What you do to one side of an equation, you must do to the other side of the equation, or you are absolutely going to miss it. You cannot just change one side of the problem and then move on. You got to change both sides exactly the same way. So if you're going to raise one side of the problem to this reciprocal exponent, then you need to raise the other side of the problem to the same reciprocal exponent. That will take care of your exponent off of your unknown variable, and you should be in the clear to finish solving the problem. The other issue came about that maybe it was the reverse problem from what was above. Maybe this time we know the base, but we do not know the exponent. Okay, so in order to solve for the exponent, we have to get the exponent down, or get the variable out of the exponent, and the only way that we have to do that is to take the logarithm of both sides. Now again, please just remember, logarithm is a mathematical operation, so if you apply it to one side of an equation, you absolutely must apply it to the other side of the equation. Okay, now we're going to learn more about the logarithms in the next unit and how they function, but for now, just understand that logarithms have the power to remove a variable from its base and pull the variable down into the base itself. Okay, so as you can see on the second step and the third step there in the green type, by applying the log to your base with your variable, it has the power to take the variable off, or take the exponent off of the base and put it down in front as a coefficient of log of whatever your base was. Okay, from there, everything in your problem should basically become numbers. Some of you have done a very poor job of solving the equation from there. Okay, but guys, log of a number is a number. Okay, this is not anything really earth-shattering. It is simply a number that is being multiplied times our variable. How do you move a number that's being multiplied times your variable? You divide it, just like any other number. It just looks strange because we're not used to seeing logarithms in a problem. But if it's just a number, it's just a number. Stop freaking out about it. Get over it. Learn how to solve it. Anyway, that's pretty much where we got to. The only thing that we did beyond that was to look at the different representations of exponential functions, which is nothing more than me taking my best guess at what additional type of problems they might decide they want to throw at you on the test. So you should still have that assignment. It is not due today. It will be due at the test on Friday. But as we talked about in class yesterday, having extra time on it won't necessarily mean that any more of you will do it. The same of you that are going to do it are going to do it. The same of you that won't do it simply won't do it. It won't matter if I give you 1 day, 1 week, or 1 month. You're still not going to get it done if you're not going to get it done. Anyway, so that about concludes the review. You can always look back at the original recordings on the lessons if something that I talked about just now is not settling well with you. Look back at the original lesson, look back at the original examples, and of course, come in for extra help if you need it. We'll see you at the test.